Alright, so this is basically what we're trying to do on this video is find irrational and imaginary roots, or complex roots, sometimes people call them. I don't know why that won't really scribble that well, but that's okay. But hopefully you found already integer, whole number, and rational roots. So this is like an x plus 3, right? You found that as a factor or as a root. Eventually, you probably found these pretty easily. 2x minus 1, like the root is actually 1/2, but it's going to be written as a fraction. So the rational root theorem was this. That's what we just kind of covered. And now we're going to get into irrational and imaginary, and throughout that time we're going to continue to solidify the rational root theorem and factoring, which is how you usually find these types of numbers. So anything with a degree of n will have n complex roots, and so now we're trying to find all of those. So let's just kind of just jump into it. For starters, if we look at the highlighted problems and we try to find a polynomial with these zeros, all you need to do is take it, switch the sign, and then this one's going to be a little strange. So actually what I'll do is we'll just kind of move this over a little bit. Okay. So the first one, so this is the whole root, you see. So you need to have x plus 2 plus root 5, which you could put in parentheses if you like. And then you have to have x minus, I guess in this case you have to put in parentheses, because you're subtracting both things, 2 minus root 5. So just so you know, like this still can be a thing. It's just a little sloppier looking. So that's pretty much all that was for. And then, in addition to that, we have right here a double root. So again, we could write a polynomial with a root of 5. That's no problem. And we could write a polynomial with a root of 3. That's no problem. Switching the sign, and because it's multiplicity of 2, that would be our double root right there. So again, you don't need to FOIL this out. I mean, you could, and you should be able to, but I'm not going to ask you to do that very often, so I don't think it's a very good use of time. So now what we're going to get into is irrational zeros, and those are going to be, they're going to be much more difficult, perhaps impossible, to find by factoring. Not impossible, but I don't really like to use factoring for that reason. So what we need to do is we need to find all of the zeros. So step one, so if you want to think about this, logically, it's like, can I factor? Like, no matter what, if you can factor, you should. So take a look at this one. Since it's to the fourth, to the second, and then to nothing, you probably can factor with an x squared and an x squared here. So let's just take a minute and think about what the factors could be. Okay, so I just try to think of this as 6 times 3 is 18, and 6 and 3 adds to 9, so I think we're going to factor into this. Alright, so here is where we get into, now we have factored it, yes? And now we have to ask ourselves, can we factor further? Like, technically, you could factor further, but sometimes, sometimes if you can't factor, you're going to need to use the rational root theorem. So you can factor, and in this case you did factor. You could use the rational root theorem on this first part, but because you could factor, didn't make as much sense. Now if you wanted to use the rational root theorem because you couldn't remember how to factor this, that would be okay. Now you could use the rational root theorem on either of these if you wanted to, but what's your best, most efficient way to solve it? Like, you got to think about all the different tools you have in your toolbox. So now the next simplest is to solve by square roots. And then below that, which I think is a lot of work, is to solve by the quadratic formula, QF, we'll just say. So in this case, right, now we're just reviewing, we're remembering that we could just set this to 0, which means that we'd have x squared equals 6, and we'd have x equals plus or minus the square root of 6. And that's it. We found 2 roots right there. That's 2 roots, by the way. And that means that x squared equals 3. That means that x equals plus or minus the square root of 3. So this is something new, but it's also something old. So it's kind of like we're mixing this old green part right here, which is also new. So it's new this year, but it's old in the sense that it's an Algebra 2 topic. So I think question 2 is going to be similar to that. So in the idea of keeping the video short, we can skip 2. It does have a very similar vibe, if that helps. Okay, so let's go to 4, since it's just a little more challenging. So 3 is similar to 4. So in other words, I would say that this problem is similar to this problem, and this problem is similar to this problem. You see 4 terms, so a lot of times you know that you can factor it by grouping. So what you can do is you can, oops, sorry about that, keep grouping that like that. Watch out for that negative that I kind of hid in there. So 3x squared times x minus 5. Can I factor? That's the question, and I think we can. Minus 4 times x minus 5. So we will wind up with something factorable, which is good. And so we'll get 3x, sorry, I keep hitting something. 3x squared minus 4 times x minus 5. Okay, so definitely one of our roots is x equals 5, so that's good. And now we're just working on this problem right here. Could solve by square roots or quadratic formula, but again, you don't really want to. So again, just to take it one step further, we're setting this factor equal to 0, but almost never, we'll almost always skip to this second line, the second step here, and sometimes we'll even try to skip to here. So that means that x is equal to plus or minus the square root of 4 over 3. The square root of a fraction is a fraction of square roots. In other words, x equals plus or minus the square root of 4 over plus or minus the square root of 3. So I guess that x is equal to plus or minus 2 over the square root of 3. That plus or minus is kind of covering us on the top and the bottom, if that makes sense. We should rationalize the denominator. However, it's not like a thing that is like life or death in real life. It's not really something you can't have, it's just something we don't allow you to have. So there you have it. That's 3 roots because of the plus and the minus. You should be able to write that as a factorization based off of what we just talked about on the previous page. So 3 roots because it's a cubic. Very good. So we haven't gotten to solve by the quadratic formula yet, and we haven't had to use the rational root theorem. Here is the quadratic formula. Take a moment to pause and write this down if needed. Negative b plus or minus the square root of b squared minus 4ac all over 2a. And it obviously only works for quadratics, meaning that this exponent must be 2. Highest exponent's a 2. Okay, so it's clearly trying to hint that you need to use the rational root theorem here. This one I thought was pretty brutal, okay? If you do wind up attempting that one, I want to say like it's either x equals 5 as a root, or maybe it's x equals negative 5. One of those is a root. So if you do attempt 6, just keep that in mind. I'm not going to attempt it right now. So we're going to now go to the rational root theorem because I see that this can't factor. Do you want to try to factor it just to see why? You can try to, but it won't really work. So if you like try to take out an x squared, for example, there's definitely something going on with my pen, which is not ideal. X squared, x minus 2 minus 18. Oh, does this work? Maybe it does work. I mean, it does say list all possible zeros, but we might be able to get out of this. So x squared equals 18. X equals plus or minus. That's going to be the square root of 9 times the square root of 2. So it's going to be 3 square roots of 2. And then x equals 2. So it did ask you to list all possible zeros. I guess if we just list them, we're kind of covered. So plus or minus 36. Okay, 36. So 36 times 1, 18 times 2, 12 times 3. 12 times 3, 9 times 4. And then 6 times 6. I think I've covered most of them. So now I've kind of covered my bases, although it wasn't exactly what they were trying to get us to do. They're getting us to try to use the rational root theorem rather than try to factor. So with either of these, we should be able to use the rational root theorem to get there. I may have to kind of, skip around a little bit. So with this one, with 7, we have, I think, plus or minus 5, 3, 15, and 1 for our, if we know the rational roots. So plus or minus 5, plus or minus 15, plus or minus 3, and plus or minus 1. So if we try to divide, synthetic divide, with 1, so if we synthetic divide, which I'm going to have to assume that you're pretty solid at, you'll find that I think negative 3 is going to be a 0 that works. So you're going to go through until you get negative 3 is a 0 that works, which means that x plus 3 and whatever was down here, and if you do divide by the root of negative 3, I think you're going to have 1, negative 8, negative 5, and then 0, of course. We need this to be 0 to show that it's a root, to show that we found a 0. So because of that, I'm going to take those green numbers, which are the coefficients. I'm going to drop from the power of 3 to the power of 2. So I'm x squared minus 8x minus 5. So that's a minus 8x. Sorry about that. And that doesn't factor. So this is kind of what we need to understand for today, is because that doesn't factor, what do? We can't really solve that by square roots. So finally, we have to get into the quadratic formula. Negative b plus or minus square root b squared minus 4 times a times c all over 2a. I have to assume that you're pretty good at this, and so you need to kind of, put the time in to get there if you don't feel that way. So this is 20, so that's going to be the square root of 84, and that's still going to be over 2, and the 8 over 2 is 4, so that's how I got 4 here. This is 4 plus or minus the square root of. Now, I know that 84 is 4 times 21, so for those reasons, it's going to be 2 square roots of 21 over 2, which cancels. So our other zeros should be 4 plus or minus root 21. So there's some of the zeros, and then the other 0 is x equals negative 3. So x equals. So those are our 3 zeros, and we should be able to write the factorization with those if and as needed. So very similarly, we're going to have this one, and I think these start out pretty straightforward in that you can even factor here, I believe. So let's say this is x squared. I factor with the 6 and 2, negative 6, positive 2. So here I have x squared equals 6, x equals plus or minus root 6. So those are 2 of my zeros right there. And here I have x squared equals negative 2. So x equals plus or minus the square root of negative 2. But negative 2, you cannot get a real solution for that. So you have to be plus or minus I root 2. We took the negative out. And those would be your other two zeros. So it's a fourth power, and we have 4 zeros. So presumably numbers 2, 3, and 4 are going to work very similarly to that. And then what you'll probably see is that you'll need to use the quadratic formula on a couple of these. So let's see how we do on on 5 or 6. I think 6 is looking a little more difficult, so let's just go for that one. I'm hoping I could just factor by grouping right now. So at 3x minus 4, and then can we take out a 12 maybe? 3x minus 4, oh that's good. So x squared plus 12, that's going to be the one that has your imaginary solutions, and 3x minus 4. So we know that one of our answers is x equals 4 over 3, because we are going to, basically that's going to be equals 3x equals 4, and this will be 4 over 3. And then this one is going to be x equals, or x squared equals negative 12, x equals plus or minus the square root of, always remember the plus or minus, negative 12, and that means plus or minus I root 4 root 3, because 4 times 3 is 12. So x is going to equal plus or minus 2I root 3. And that should be it. Those are your zeros. So be aware that you could have to use it. You may have to use the quadratic formula, and then finally wind up with those imaginary solutions. Okay. So that covers all of complex and imaginary zeros. So our options are factor, which it seemed like that happened a lot today. Use the rational root theorem, the rational zero theorem, I guess. And then if you don't get either, if those don't, one of those top two should probably work. I think 99% of the time. I don't want to say it every time, but if you can't factor it, you can probably use the rational root theorem. If you can't use the rational root theorem, you could probably factor it. And so anything you can factor, you could use the rational root on. So that's kind of helpful. And then once you get past that, you're probably going to be into a situation where you're here, okay? Now, keep in mind, you may need to go back and factor again. So like what could happen is you use the rational root theorem, right? You get here, and then it like returns to can I factor? So it's possible that you get into this like a loop that loops back up. But it's also possible that you keep moving down and you try to solve by square roots and by quadratic formula. So between all of these four things, you should be able to find all of the zeros. All of the whole number zeros, all of the integer zeros, all of the rational zeros, all of the irrational zeros, and all of the imaginary or complex zeros. Okay, long video, so I'm going to end it there. Hopefully I can edit out some of that stuff in the middle, but if I didn't, I apologize for that. Okay, that's it.